maybe we should skip the fraction things, but we're going to give it a try. So with fractions, we've got, you split something in half, and so you have to represent this somehow. So here we cut it in half, we take a portion of it, and we have to represent this portion somehow. So we're going to say 1 out of 2. This is basically the denominator tells you what is the unit. So one of the things that happens frequently when you have when you're working with people as they're first learning mathematics is that they don't necessarily know when they're supposed to be able to add something and when they're not supposed to be able to add something. So for example, they may understand that adding 3 squares and 2 triangles, that this isn't something that can work very well. Like, how do you do this? Or like, what is 3 oranges in 1 car? What's the sum of 3 oranges in 1 car? Then in that case, it's kind of obvious that you don't add them together. But then when you come to things like 3x plus 2x squared, it's not as obvious. Like, can I add these together? Is this 5x3, which would be one of the common ways of doing it, 5x cubed? And the answer is no. But like recognizing that these two things are actually different. This would be like saying, what is 30 plus 200? In which case you recognize that they would be in different columns in the number. Or you can say, this is 3 feet and 2 acres, because feet is got units, linear units, and acres has square units. And so 3 feet and 2 acres is also something that's not added together. And so recognizing this is a term that has a given unit or some variables that aren't known, and you can only add terms that are like, where all of the bases or all of the variables match from one to the other. So the same thing happens basically with fractions, where you'd say like, okay, this is 1/2, like so 1 times a half, or it would be like 3/2. Okay, so where the half is kind of like a unit. So if you have a half and a third, you can't just add these together. It's not 1/5. It's not equal to 1/5 because you don't just add the denominators. This is like saying 1 apple and 1 orange. How do they add together? You have to come up with a way to combine them. And the way that you come up to combine them is that you find the common denominator. This is going to be important later on when we're getting more complex things, complex fractions that we need to add together. So you have to come up with something that they share and then transform to a representation where they share that thing. So in this case, these two things, you find the least common multiple. We saw how to find the least common multiple, where you take all the factors and you line them up, and then you take one of each factor. But in this case, it's just 6 because it's just multiply across because they're both prime. So the common denominator is 6. You multiply the top and the bottom by what is missing from 6. So you recognize, okay, I'm going to end up having something. I'm going to end up having something over 6. And that means I need to multiply the top and bottom here by what's missing, 3 over 3. And that gets me 3/6 plus, and then here you have to multiply by what's missing again, which is 2 over 2. And then that's going to give me 2/6. And then in the end, I'm going to get 5/6. That's a 6 right there. Okay, so what did we just do here? We transformed these things. We found an equivalent number. So technically, a half is not, it's not identically equal to 3/6. It's mathematically equivalent to it, but they're not equal to each other, because if they were equal to each other, then this would be a 1 and this would be a 2. Instead, they're mathematically equivalent. They have the same value. And so you're basically taking something that is not the same thing as this, and you're transforming it into something that has an equivalent value to this thing, but has a different unit, or different way of measuring, different denominator, so that you can then say, okay, these things are now like, the denominators are alike, therefore I can add the numerators together, which is the same thing as saying I'm going to transform into some basis where now I can add things directly the way that I normally think of adding, and I'll stay in that basis when I'm done. Let's see, how do I draw my pie chart outline in such linear sections? I do not know the answer to that question, but I did. So something to keep in mind when you're dealing with fractions, you're finding some equivalent representation that makes it so that you can actually add, because now the denominators are the same. All right, let's see. What else do we got going on? Okay, so now this, talking about the real numbers and the complex numbers. We've already seen the real numbers, we've seen the rational numbers, we've seen the integers. One thing that hasn't that I haven't shown yet, or like that we only briefly talked about, is the nature of inverse functions. So, for example, if you have, eventually we're going to get to the point, it's actually in the next chapter, where we're going to be solving equations. And let's see, before we do that, never mind, we're going to skip that part. We're going to come back to it in a minute. I'm going to finish out just what's in this chapter, and then eventually we'll revisit it. Okay, so this last part of this chapter is going to be looking at square roots. What does it mean to have a square root? So a square root is another, raising something to a power is another binary operation. So we've already seen addition, we've already seen multiplication, and now we're going to have a new binary operation, which is raising something to a power. So you take two numbers, 3 like this, and now you say, okay, this is I take two integers in this case. They don't have to be integers, they could be real numbers. I take two numbers and I come up with a formula or a mechanism that will transform this into something, some third number out of my original set. So it's a closed binary operation. It's associative, so I can do 3 to the second to the, what am I going to do? Well, also to the second, I guess. So this is going to be what? I can associate these. I could, for example, I can do it in one of two ways. I could do 2 squared is 4. Let's see, is that going to be a good way to do it? Yeah, okay. 2 squared is 4, so that's going to be 3 to the 4th, which is going to be 81. Or I can do 3 squared, which gives me 9 squared, which is also 81. So you'll notice that these things are associative. I can group it like this and evaluate raising something to a power, or I can group it like this and do this one first and then do that one after. What I cannot do is I cannot reverse the order. So I can't do, in this case, 3 squared is not equal to 2 cubed, because this one's going to be equal to 8 and this one's going to be equal to 9. Okay, so this binary operation of raising something to a power is not an, what am I trying to think? It's not a commutative binary operation the same way that multiplication is commutative or addition is commutative. Does it have the other things? Does it have an element, a power identity? Let's see, does it? I don't know, maybe it doesn't satisfy groups the same way. Let's see if it satisfies the things of a group. It seems the more I think about it that the answer is probably no. So it probably has some other name associated with it, the raising of the power. But let's see if it has these things. So is there an identity? So 3 to the 1 is equal to 3, but that's not the same thing as 1 to the 3 is not equal to 3. That's equal to 1. So the identity doesn't work from both directions. Okay, so it's not a group, but it was a good thought, at least while it lasted. But it is another example of a binary operation. It just doesn't form the same mathematical structure that addition and multiplication do. But it's still a binary operation. It's not commutative. It is associative, but it doesn't have identities associated with it. Like there's no, the identity that you can put from this side up in the top part is not the same identity that you put in the bottom part, which is not true for addition and multiplication, because 3 plus 0 is equal to 3 and 0 plus 3 is equal to 3 also. So in the group structure that we get from addition and multiplication, the identity works in both directions, and in this case it doesn't. So there we go. It's a different algebraic structure than a group. One of the things that's important to recognize that when we're working through this algebra system is that we're actually not working with groups, which is kind of a simple algebra. We have a more complex algebra that involves both addition and multiplication. So we have 3 times 2 plus 1, and we have something like this. And so we need to understand how to resolve situations here where you have both operations that are active. Which one do you do first? Do you do 3 times 2, which would be, so if you have these different operations acting at the same time, then you can't associate it anymore, right? Your plus and times don't associate with each other. They don't commute with each other. So if I did 3 times 2, I would get 6 plus 1 would be 7. Or if I did the 2 plus 1 and got 3 times 3 is 9. So if I do this the way that you're supposed to, then I get 9. And if I do it the way that you're not supposed to, where I just start from here and then work my way across, then I get 7, right? 3 times 2 is 6, plus 1 is 7. And so there has to be some rule about how do you treat these different operations when they're happening in the same expression. And in that case, we have the order of operations, which I didn't use this acronym when I was taking math classes, but it's Pemdas. Okay, so that's what? It's parentheses. So you resolve parentheses first, and then you do exponent second. So if this was squared, then you would do the exponent. And then you do multiplication and division, which is actually the same thing. And then you do addition and subtraction, which is also the same thing. So I didn't use an acronym. I didn't use an acronym. We just learned it because we were smart that way, or we were just had more people that were bad at math, and so it didn't matter if they learned it or not. Yeah, so we didn't do any have any kind of tricks. It was just, here's the order of operations, and do it right, or else you'll get the answer wrong. That was kind of how I was taught. So that's important to recognize. There is an order of operations that's established when you say, these are the two operations that I have. Here's how one affects the other. A few other things that are important about multiplication is that because of this order of operations, multiplication distributes across addition like this. Okay, so this would be the equivalent. This 9 is the equivalent of 3 times 2 plus 3 times 1. Okay, that also gets you 9. And so that shows you the distributive property. How do you treat, when you have these two things next to each other, is there more than one way to get to the right answer? Either you can go PEMDAS and get this reduced down to an integer and then do the integer multiplication, or you can have some mechanism that preserves this order of operation, but it does it through some other use of the notation. So you have this notation, you apply the notation in a particular way, and you end up with a result that is equivalent of doing the order of operations, but for one reason or another, it happens to be easier to work with. This is also, of course, without this squared up here. One more thing to discuss, and that is what it means to have an inverse, or what it means to have a root. So we need to talk about roots. So there are numbers that we've already talked about, prime numbers and how those things can factor, but we haven't talked about square numbers. So if you have a composite number, like say 6, so 6, you can draw 6 in a variety of different ways. So this goes back to those rectangles that I drew before, where a prime number like 5, you can only draw rectangles like this. That's not 5. 1, 2, 3, 4. So this has 5. You can only draw rectangles that are like that or that are vertical. So this is prime numbers, but composite numbers you can make multiple rectangles out of, different kinds of rectangles. You can have one that is like that, 6 across. That should be 6 across. Or you can have one like this, that is a 2 by 3 rectangle. And there are some special numbers where you can make a square out of it. Okay, like 9. Well, that's an ugly square. So 9 you can make a square out of. And so there is a mechanism to say, if you have a square number, then what is it that corresponds to the length of the side of that square, and that would be the square root. So if you have any number that's multiplied by itself, 6 times 6 is going to be 36. It means that you can represent it as a square, and that there is a way of transforming from the square to the length of the side, which is the square root of 36, and then that gets you back to 6. We will see in a moment that this is not the only square root of 36. There are a few square roots of 36, 2 of them. There's also an issue where if you have a cube, so like say you have a 3-dimensional object, so we'll do one that's got 2 sides. So here's a 3-dimensional object. It has, in this case, 8 little cubes in it. And so this has a cube root, which is the length of the side here. So the cube root of 8, in this case, is 2. The same thing if you have a 4th root. If you had a 4-dimensional hypervolume that was uniform in all directions, then it would have a 4th root, and et cetera, and so forth. It turns out that while there are 2 square roots of something, there are 3 cubed roots and 4 fourth roots and so forth. And that's actually the fundamental theorem of algebra. We will get to that, it looks like, later in the text. All right, I think that clears up everything from chapter 1, and I may end up having to go back and revisiting some of this because it isn't always clear what is, well, this is my first time through the book, so it isn't entirely clear if there's going to be some interesting aspects of algebra that are skipped in the first couple chapters simply because, well, not every cool thing that's in algebra makes it into the introductory textbooks, even though it should. So let's take a look back where we were at the beginning. So we should be moving on to chapter 2 now. I'm going to drag this up here so I can get to chapter 2 and see what's going on with chapter 2, which should be solving linear equations and inequalities. All right, so this is going to be looking at solve equations using subtraction and addition properties of equality, solve equations using division and multiplication properties of equality. We can do those at the same time. Solve equations with variables and constants on both sides. Okay, no problem. Use a general strategy to solve linear equations. Okay, no problem. That's basically what we'll do. So this chapter might be really short. Solve equations with fractions or decimals. Also, that's the same thing. Solve a formula for a specific variable. Now that's going to be a little bit different, so that's going to be useful. And solve linear inequalities. Okay, so far so good. That doesn't seem so bad. All right, let's get started then with linear equations. So in this case, when you have an equation that's set up, a linear equation is something where all of the variables have powers of 1. So we've talked about how you might have like 3x for something, 3x. So in this case, the exponent here is equal to 1, and that's what makes it a linear equation. If there was an exponent here that was something else, then it would not be a linear equation. And the fact of the matter is that if we remember the fact that you can raise things to different powers, one of the things that's useful to note as we're going to show these expressions is the following. So if we have 2, and then you go 4, 8, 16, these all have equivalent representations, right? So this is 2 to the first. So if we look at the exponent representation, this is 2 to the first, this is 2 to the second, this is 2 to the third, this is 2 to the fourth. And then if we go the other way, so we're cutting things in half, then we get 1, a half, a fourth, an eighth. And so this is going to be what? So the notation, this is a notation thing. It doesn't have to necessarily be written this way, but this is the way that we have all collectively chosen, we the mathematicians, which I'm a physicist, but that means that I get to make all the rules too. The notation that we use is that this one will be 2 to the minus 1, 2 to the minus 2, 2 to the minus 3. And so the only thing that's missing here is 2 to the 0. So this structure, or this notation that we have using exponents to represent these different numbers, is going to be useful when we're solving different kinds of equations. Now, when you have an expression is just something, right? 3 is an expression, 3x is an expression, 3x cubed y squared is an expression. It's an equation when there's an equal sign. There's no equal sign in any of these things. There's nothing to solve. You might be able to simplify an expression. So you have a whole bunch of stuff and you want to simplify it and make it in like what's the simplest equivalent representation of all of these things. And so you do whatever it is to manipulate the exponents and divide things out and factor stuff and cancel it, whatever the case may be. So simplifying an expression is the best you can do. But that's not the same thing as solve an equation. So an equation is when you take two expressions, 3x, and you set it equal to another expression, 4x plus 1. So an equation, you take two different expressions that are not necessarily related to each other, and then you force them to be equal to each other by saying these two things are equal. And then the idea is to try to find where are these two things equal to each other. Like under what conditions will this expression, which does not look the same as this expression, I think everybody recognizes that these two expressions look different. Under what conditions will these two expressions be equal to each other? And in this case, there's only one thing that you have that you're able to manipulate or to adjust, because these are just they're just integers, or they're coefficients. The only thing that is variable that you can choose a value for is this quantity x. And so when you're dealing with an expression, or I'm sorry, when you're dealing with an equation, you're going to say, what are the conditions where these two expressions are equal to each other? The only thing that I have that I can even change the value of to allow it to be equal to each other is by adjusting this variable. And so you solve for this variable to see, is it possible for me to find a value for this variable that allows these two things to be equal to each other, mathematically equal to each other. Symbolically, they're already different. Is everything equal or only specific numbers? So in this case, a question that one might have is there only one solution to where these two things are equal to each other? So let me give an example of what this is talking about. If suppose we have, we haven't gotten into graphing lines yet, but we're going to skip ahead. So if I'm going to say like the vertical direction y is equal to 3x, and then I'm going to have another y equals 3x, and I'm going to do another one that's going to be y equals, I'm not going to do that 4x minus plus 1 because that one is a little weird. Let me do x plus 2. Okay, so if I were to plot these two graphs, y equals 3x looks like this. Okay, it's kind of a steep line like that. And y equals x plus 2 is going to look like this, like that. Okay, so these are the two different lines that are there. This y equals 3x, so it's some representation of that line. Y equals x plus 2 is going to be this different representation, and there's only one place where these two expressions can be equal to each other. So if I'm going to say I want these two things to be equal to each other, which would be the equivalent of saying 3x equals x plus 2, they're already not the same. So then the question becomes, under what conditions will these two things be the same? Which is, for what values of x will if I evaluate the left-hand side and if I evaluate the right-hand side, will I get the same answer? So, and then graphically, it's the equivalent of seeing where these two lines intersect. That's the state of all possible cases. These are all the cases where this equation can be true, where these two things are set equal to each other. But you can imagine easily, you have different geometric shapes. So suppose you have like a figure 8 shape like this, and you've got a circle. Okay, so with a figure 8 shape and a circle, you can get several locations where you have an expression that gives you a circle, or an equation that gives you a circle, and you have another equation that gives you this figure 8 shape. You set those two equations equal to each other. You put them in a situation where you form two expressions. You set those two expressions equal to each other, and then you say, under what conditions can this happen? And you should get 4 answers. Okay, but it might be a complicated algorithm that you have to go through to get to those answers, but those answers are going to exist. So the same thing with, in this case, we're doing linear expressions, or setting two linear expressions equal to each other and then finding the value for the variable. What mathematicians mean when they say linear is the following. We saw how I had this, 2 to the third is 8, 2 squared is 4, 2 to the first is 2, and so forth. Well, when you have a variable instead of a number in there, you're going to have x to the 0, you'll have x to the 1, x squared, x cubed. You might have x to the minus 1, which is going to be equal to 1 over x, right? Because it has the same rules, right? 2 to the minus 1 is equal to 1/2. You might have x to the minus 3, which is going to be 1 over x cubed. Okay, so it uses the same notation. Whatever notation works for numbers, the same notation also has to work for variables. Otherwise, you don't have a consistent notation system. So a linear equation is an equation where you have expressions that are set equal to each other, and those expressions can only involve multiples of these two things. Okay, you have your variables, and you can only go up to powers of 1. So you can have powers of 0, which is going to be it's going to be just a number because things raised to a 0 power is equal to 1, right? 2 to the 0 is equal to 1. So linear expressions mean that you can have constant terms, which are proportional to a variable to the 0 power, and you can have linear terms, which is coefficients times a variable raised to the first power. Anything above that is going to be quartic equations, cubic equations, or quadratic equations, cubic equations, quartic equations, or whatever. So the power, the highest power in your expression that you're going to inject into this equation is the order of the equation that you're trying to solve. So one of the things, I guess this is a good place to bring it up. We'll see it later on. But there's a thing called the fundamental theorem of algebra. Fundamental theorem of algebra. Okay, I know that's kind of hard to read, but that's what it says. Fundamental theorem of algebra. And the fundamental theorem of algebra says that when you have an equation of a given order, so you might have an equation that is, now what an equation, in this case what they're talking about is something like a coefficient times x to a power, like 3, plus another coefficient. Let me put a subscript on the coefficients. A squared, a sub 2, x squared plus a sub 1, x to the first plus a sub 0, x to the 0 is equal to 0. Okay, so you say you take two expressions of different x with different total terms, a variety of terms, you manipulate them so that they're all on one side, and you end up with an equation that looks like this. Okay, this is the standard form or that you have for polynomial equations. So you have an equation, a polynomial expression set equal to 0. That's the most common way that these things are written down. Some polynomial expression set equal to 0, and it has some maximum power right here. So in this case, the maximum power is 3, but it could be something else. All of these a's that are out front, those are just numbers. So it could be a 3, it could be a 2, it could be a pi, whatever. Actually, it can't be a pi. In general, these things are written with integer coefficients. And I guess in principle, it could also be an irrational coefficient like pi, but integer coefficients are the ones that are usually invoked. Nevertheless, the point being that the fundamental theorem of algebra says that whatever this maximum power is, this equation will have at least, or will have exactly this many solutions. Okay, that's like saying I have, what are the conditions where this equation is going to be satisfied? Those equations are going to be given by values of the one thing that I can tune, which is the x. So I can tune the x, I can change it to any value that I want. I can't change the numbers that are out front because those are fixed, right? Those are just coefficients that are decided by either nature or the user or whatever. But this is a variable. I can adjust this variable to make certain that these two things, or that this expression on this side is equal to 0. The fundamental theorem of algebra says that you will get more than one solution. In fact, you'll get this many solutions. Whatever the highest power is, that's the number of solutions that you will have. So for example, if you have an equation that looks something like this, and we'll get more into detail with this a little bit later, but x squared equals 4, what number, if you square it, is equal to 4? The answer to that, of course, is 2. But the fundamental theorem of algebra says that, look, this is a factor of 2 up here. There needs to be 2 solutions to this. There have to be 2 solutions to this equation, or else the fundamental theorem of algebra is wrong. And if you have a theorem, so just for a terminology, if you have a theorem, it means that it's something that has been proven, as opposed to an axiom. So an axiom is like a supposition. It's what you assume to be true. Sometimes they're called postulates. So axioms and postulates are the same thing. They are the things that you say, these are true by definition, or I'm going to assume that these things are true, or assuming that these things are true, what are the things that follow from that? So given all the mathematical structures and things that we have, those are all axioms, like that there's an associative thing, there's a binary operation, and here's the rules about how that operates. That's all just kind of put into the algebra. The fundamental theorem of algebra, a theorem is something that you actually prove based upon logical application of the axiom. So you start with some assumptions, and then you say, if this statement is true, then this other statement is true because things are associative, and if this statement is true, then this thing is true because things are commutative, and if this thing is true, then this thing is true because, etc., and so forth, and you end up with a conclusion. That conclusion is a theorem. So the fundamental theorem of algebra is something that must be true given the rules that have been imposed on this algebraic system with the rules of addition, the rules of multiplication, and so forth. And this says that there have to be, in this case, for this equation, there have to be 2 solutions to this equation. One of them is 2, the other one is minus 2. If you take minus 2 and you multiply it by itself, then you also get 4. Okay, so that shows that the fundamental theorem of algebra is correct, at least in this case. So another thing that one might then look at is, what about x cubed equals 8? So what number, if you cube it, is equal to 8? Well, one answer is obviously 2 again, or maybe it's not obvious, but one answer is 2. 2 times 2 times 2, which is 2 cubed, is equal to 8. Minus 2 is not 1. This is not a solution to this. So minus 2 cubed is actually going to be negative 8. So this is not a solution to this. So the fundamental theorem of algebra, wait a minute, I thought that the fundamental theorem of algebra said that there have to be 3 solutions to this equation. And I've only shown 1. And the other solutions of this equation come from, you have to actually go beyond the real numbers. You have to go into the complex numbers. Okay, so you have to have a superset of the real numbers in order to find the other 2 roots. It turns out that the other 2 roots are going to be equal to what? It's going to be 2 times, minus a half plus or minus root 3 over 2i. I think these are the other 2 solutions. So if I were to cube this, should we give it a try? What happens if I cube this? So that seems like a lot of work. Maybe can I do it in Mathematica? I don't know if my Mathematica is up to date. All right, here we go. Let's see. I claim that this is minus a half plus skirt 3 over 2i. Okay, and a 2 out front. Okay, and that if I take this value, it's not showing up. Let me put it down, and also let me make it bigger. What do I do? A plus, 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 like that. Not quite so big. All right, so if I take this and I cube it, okay, full simplify, 8. It doesn't look like it says 8, but it does say 8. Okay, let me see what happens if I do expand. Option says expand. Oh, it does 8. So there we go. Now, how did I know that this was here? I know that this is here because of trigonometry, and we haven't gotten to trigonometry, but we'll get there eventually. Basically, what turns out that when you have simple expressions like this, where's my thing? Okay, simple expressions like this, where it's some number cubed is equal to some constant, or some variable cubed is equal to some constant, then you find that in the complex plane, so now you have complex numbers where you have I as an allowable number. So you end up with solutions that you'll have some real solutions, and then the complex solutions are equidistant around this circle. So this is the imaginary number line, and this is the real number line. So the real numbers are along here. The imaginary numbers are along here, so that would be like 3i is going to be along there. And in this case, it was a cubed root. So I was looking for some number cubed is equal to 8. And so in this case, what you do is you say, all right, it is the solutions to this equation, the 3 roots are located some distance away from the origin. In this case, it's 2. It's the real value of that radius. So that's going to be x equals 2, gives me here. And then the 3 roots are all equidistant as you go around this circle. And so it's going to put you here so that this angle is 120 degrees. And then it's going to put you down here where this angle is 120 degrees or minus 120 degrees. So that is where all these roots lie. So for example, if you're talking about square roots, x squared equals 4, then you're going to get this one here, and then you go equidistant to the other side, and that ends up down here, which would have been minus 2. So if it's a root like this, an even root, then you end up with another another root that's on the real line. If it's, or another solution that's on the real line. If it's something that's not like an odd power, then you're going to get, for example, the fifth roots, x to the 5 equals, what is it, 32? Then you're going to end up with, here's this thing here, and then you're going to have 5 equidistant roots like that. This one, that one, this one, that one, and that one. So that's just the nature of how these things work. This is something that we'll get into a bit later when we're talking about other solutions. But that, nevertheless, even though it's not really introduced this way in this textbook because it's an 8th grade textbook, but that's kind of one of the things that you're looking at. It's one of the things that's shown in this, the real numbers section, this section 1.8 in the text, where it talks about like, what does it mean to square something? What does it mean to cube something? I think it's getting a little bit ahead of itself, but that's the way that things are. Okay, so in this case, solving linear equations. So what this is saying is with linear equations, we're going to have a linear expression, which means that you can have some variable to the first power, some variable to the first power and some variable to the second or to the 0th power. And you devise an expression made of those two components and you set it equal to another expression made of the same components. Okay, so you're going to have like a 3 and a 2, and maybe this is a +2, and you might have a -1 and a -5, something like this. And then you can simplify this. The notation allows you to simplify this to 3x. So typically when it's x to the first, you ignore this. When it's x to the 0, you just set this equal to 1. So 3x plus 2 is equal to -x minus 5. Okay, so now I've simplified these two expressions that both only included a term that has something raised to the first power and something raised to the 0th power, and now they're set equal to each other. And then the question becomes, okay, what is it? How do I take these two expressions that I am looking for the conditions under which these two things are equal to each other? And the answer is, well, what you need to end up with is the variable things on one side. So you get the variables over here, variables, and you put the constants on the other side. So variables over here and constants on this side. So somehow you have to separate the numbers, like the real numbers, the coefficients and the constants. You have to separate them from the variables and move them to opposite sides of the equation. And that gives you the solution. Okay, so let's take a look at what this means. Let's use this as an example. Okay, so I have 3x plus 2 is equal to have -x minus 5. So the only way to do this, or like officially the way that you do this, is you need to undo what's being done to each of these sides. So my thing isn't working anymore. Here we go. So how do you undo what's being done? Well, in this case, I need to get this x isolated by itself. So the way that I can do that is the first thing I need to do is move any constants to the opposite side and then move all the x's to one side. So let's focus on moving constant terms to the opposite side. So this constant term is on the wrong side of the equation. And so I say, okay, what is this constant term doing to this whole expression? What does it contribute to this expression? And the answer is that it adds 2. So how do you undo addition? The way that you undo addition is that you invoke, let me do that one more time. You invoke the additive identity. In fact, you invoke the existence of inverses to this. So in this case, this 2 is here. You don't want it to be there. And so you need to do the inverse to both sides of the equation. If you're dealing with things that are commutative, it doesn't necessarily matter where you put the inverse. But if you're dealing with things that are not commutative, so if these things were matrices, for example, which don't commute, then you'd have to apply the inverse to the correct side of the expression. So in this case, we have a 2 here. I want to get rid of the 2, and so I'm going to include the inverse of 2. So I go plus 2, and in this case, it's the additive inverse because 2 is being added, and so I need to use the inverse of the additive inverse of 2. So it's plus 2, and now I do the additive inverse plus -2. So we saw, I think it was last time, that 2 has an inverse. Every number has an inverse in this addition binary operation, and that's the negative numbers. So these two things together are equivalent to the additive identity. So I have this, I hit it because it's commutative, it doesn't necessarily matter where I put this, but if it wasn't commutative, then I would have to do this. Because I'm doing it on the left-hand side, I would have to do the same thing also on the left-hand side over here. So if this was a matrix that I was undoing, or something that wasn't commutative, if addition wasn't commutative, then because I'm applying this to the left-hand side in order to get this expression equal to 0, I would have to apply it to the left-hand side over here as well. But we're dealing with commutative numbers, and so that's not an issue. Just bear in mind the fact that this could be an issue if you're dealing with, if your field structure, like the structure of your addition and multiplication, actually involve non-commutative component. I guess if it's a field, it has to be commutative. It has to be commutative. But if your algebra is involving structures where it's not commutative, then you have to bear in mind where you're applying your inverse. Okay, so I'm claiming that this 2 is being added. If I need to eliminate that 2, I need to find, I need to do the additive inverse to the 2 in order to produce the identity element. And so I'm going to have to do the same thing to both sides. Otherwise, it's no longer an equation, because if I do something to one side of an equation, I have to do it to the other side of the equation, or else it's no longer in balance. Okay, so now I've got this -5, and now I've got this plus -2. Okay, and now I simplify these two expressions using my knowledge of algebra. So I get 3x, and now I have these, here is an element, and here is the inverse of that element, and that gives me plus 0. It gives me the additive identity. And that's going to be equal to, and now I just use the rules of addition here, minus x minus 7. So -5 plus -2 gives me -7. And I don't have an eraser, so we're going to have to deal with this. So let me write this now at the top. So I've got 3x plus 0, 3x plus 0 equals -x minus 7. Right, now I have these two terms that are being added together, and one of those terms is the additive identity. And what I know about the additive identity is that when I add the additive identity to an expression, I just get that expression back. So this is like the nuts and bolts of what you're actually doing when you're solving these linear expressions. So I have this additive identity, I'm combining it here. The rules of addition with the additive identity tell me that this is equal to whatever is there. It also has the assumption that this 3x is going to be part of that number system because it's a closed binary operation. Okay, so now I have -x minus 7. All right, so now all of the constants are removed from this side and moved over to the other side, and then I have an equivalent number over here because I know how addition works. Now I need to get this one to the other side. So the way that I'm going to do that is I need to add the additive inverse of this one because it's its own term. And so if you want to undo a term, you have to do addition. Terms are things that are separated by addition. And so if I want to get rid of this term from this side, I have to use the additive inverse. If it was a factor that I needed to get rid of, then I would use the multiplicative inverse. But this is a term, and so I'm going to use the additive inverse. So the additive inverse of -x is going to be equal to +x. So I'm going to get 3x going to be equal to, that's an x right there, is equal to plus x. So that's the additive inverse of this, plus, in this case, -x. Okay, so that's -x, I'm just separating by a plus sign, minus 7. Okay, if I'm going to add this to this side, I have to also add it to this side. Technically, it's I should be adding it on the same side of the expression, but as I mentioned before, these things are commutative, and so it doesn't matter in this case. But there are situations in the vast universe that we live in where it does matter what side you do the addition. Okay, so now x plus -x is going to be equal to 0. So now I've used the rules of algebra to give me the additive identity, which is going to be useful in a moment. And then over here, I know how to add these things together. I've got 1 apple and 3 other apples. That gives me 4 apples. Okay, and these are still equivalent because I've done the same thing to both sides. Okay, so now I do the rules of addition here, and I get 4x equals -7. Okay, so far so good. All right, the next thing that happens is that you go, how do you isolate x on its own? So we've finished the addition part, and now we need to do the multiplication part. Okay, So in this case, it's interesting. Is this something that happens each time where you always do the addition first and then you do the multiplication at the end? No, it doesn't happen all the time. With linear expressions or linear equations, it does. With quadratics, it might. Radicals are different, but I think with anything shy of... No? Okay, so with linear expressions, it works this way. All right, so let's take this one and see where we go from here. So now I got 4x equals -7, and now I just need to get rid of this 4. So 4 is now being multiplied, and so now I need to use the multiplicative identity and multiplicative inverses to get rid of this 4 and move it somewhere else. So how do you get rid of this 4? Well, I need to multiply it by the inverse of 4. So that's going to be 4 inverse times 4x equals, and then it's going to be 4 inverse on this side times -7. 4 inverse looks like this. So what is 4 inverse? Well, one of the things that we saw earlier is that when you have, this is kind of standard notation for inverse, is to put a -1 up there or to have something to the negative power. So note that 4 inverse is equal to 1/4. Okay, so this is just this is another way that the notation works, and it's useful to use the notation this way because things can get really complicated, and this is the notation is, it's clunky when you're just dealing with numbers. It's really powerful when you're dealing with things that are more complicated than numbers, sticking with the notation. So 4 inverse, this is the multiplicative inverse of 4, and you have to do it to both sides. And in this case, I'm also going to continue to do it from the same side, although, as I said before, it doesn't matter because multiplication is commutative. All right, so now now I use the associative property to say, oh, here's 4 times 4 inverse. 4 times 4 inverse is 1. That's the multiplicative identity. So I've got the multiplicative identity here, times x is equal to 4 inverse times this, and then the rules of multiplication just say that that's going to be -7/4. Okay, and then the last step is to say, oh, the multiplicative identity says that 1 times whatever it is going to be whatever it is equal to -7/4. That was a lot of steps to solve one simple equation. So you start with a series of terms. Those terms are all equal to each other, and what you're doing is invoking the rules of the algebra that you came up with to begin with. So the rules of the algebra that we came up with, like the rules of the operations that we came up with, is that there is an additive identity. There are additive inverses, that those things are associative. In this case, that those things are commutative. There's also multiplicative identities. There's also multiplicative inverses. There's also multiplication is associative. It's also commutative. And those are the only rules that you can apply when you're trying to solve these equations. Trying to find what are the values of x that satisfied that original expression, or that the original equation where two expressions were set equal to each other. And so it isn't normally what we think about when we're solving these kinds of things, that we're actually invoking the really fundamental rules of algebra in order to reproduce this, but that is actually what's going on. So it's binary operations and then the simplifications that come throughout the process. So any linear equation, a x plus b is equal to 0. So this is kind of a general form of writing this down. So this is a linear equation. What we had before, which was 3x, what was it? 3x plus 2 equals minus x minus 5. Is that what we had? I can put this, I can use the rules of algebra to get this equation into this form. If you don't believe me, watch. It's going to be amazing. That's going to be 4x plus 7 equals 0. So I can, using the rules of algebra, right, I can add this, I can add 5. I can use the additive inverse of this one. And then I have to add 5 over here. That gets me to this 7. I have to do the additive inverse of minus x, which is going to be plus x. And I go plus x over here, and that gives me to 4x. So I can put any linear equation or any two linear expressions that are set equal to each other, I can put it into the form where it is a single linear equation that has this form. Okay, so then what's the answer going to be? So in general, ax plus b equals 0 is going to be what? Well, I need to isolate this x by itself, and the way that I do that is I use these inverses and the identities that we have. So I'm going to get ax plus b plus negative b. equals negative b. Okay, so I have the additive inverse here. That gives me a 0, and this gets me minus b. And now I've got ax plus 0 equals negative b. I know how to simplify this because addition is a binary operation, and I know that when I'm using the additive identity that I'm going to get this return, so I'm going to get ax equals minus b. And now I have a multiplication issue. So I find what's the multiplicative inverse of a, which is going to be a inverse, and I multiply both sides. I'm going to invoke the commutative property here and just do a inverse on that side, although if these were matrices that wouldn't work. You would have to do it from the same direction. And now I've got these two things. I can associate these together. That gives me a 1. That's the multiplicative identity. 1 times x is going to be equal to minus, so technically it's going to be minus a inverse b. That's the actual direction that I did it from. And then I get x equals minus b over a. So this is also invoking the notation. Or in other words, it's going to be x equals minus a inverse b. That is the general solution. So anytime you see an equation that looks like this, that's the solution. You just write it down. It works for everything. Let's see. If you barely know math, hey, everyone starts from somewhere. I didn't know math. My worst grade in middle school was algebra. So this was actually my worst class, except for penmanship. Penmanship, I got a bad grade, but I don't know if they even grade penmanship anymore. But that was also in 3rd grade, and that didn't count. So anything above, once I got into middle school, this was my worst class. So, but that's kind of weird, right? This isn't the way that we normally think of it, especially once you get used to it and you're like, well, this is the rules that you follow. You don't necessarily realize that you're actually following even more fundamental rules in how these equations get solved. So that's pretty gnarly. All right, let's see if there's anything else from this chapter that I'm missing. Solve equations with variables and constants on both sides. Okay, we did that. Solve equations using division and multiplication properties of equality. I wonder if it actually, let's take a look and see if the book actually treats it the same way that I treated it. Okay, let's see if it invokes these rules of algebra. Determine whether a number is a solution to an equation. We don't need to do that. That sounds boring. Okay, so that's the solution to an equation question. Oh, so they have these interesting, let me get rid of this so that that can get a little bit bigger. Interesting figures that's like envelope, which is the unknown, plus 3 is equal to 8, and then how many things are in the envelope? That's pretty clever. I can dig that. So we took away 3 from each side, then we were left with 5. It doesn't seem to be... Okay, so that's its model. Let's see if it invokes the actual inverse and stuff, because otherwise why cover it, right? Why cover that it's associative if you never use the associative property? Okay, so this is the equality thing that says that you can do it on both sides. You undo the addition of 37 using the subtraction property of equality. The subtraction property of equality, I guess, is this thing right here. Here's the subtraction property of equality. But they don't have to actually say it this way, right? You don't actually have to call this the subtraction property of equality. You can just say that you can do a binary operation with inverses. And so you don't even have to come up with a new name. So, I wonder which one is actually, calling this an actual property. I wonder which one actually would do better with elementary school kids or junior high school kids in this case, to invoke this subtraction property of equality, which isn't really a thing. I'd have to think about that. And instead just say, here's an inverse, and you're adding the inverse so that you can get to the identity. Because it doesn't even say that you arrive at the identity, right? Nowhere here does it say that you get to the identity. The addition property of equality, that you can add things to both sides. Okay, well, I haven't been through an 8th grade algebra textbook since I was in 8th grade. So it's interesting to see what it is that they show and what it is that they don't show as they're going through how to do these solutions. Okay, then you can do it with, not only can you do it with integers, but you can do it with real numbers. So real numbers would be represented by decimals. You can do it with complex numbers. Simplify, okay, so here's the steps. Simplify the expression on each side as much as possible. Okay, so that's like, using the associative property to combine like terms. One thing to recognize is that subtraction here, I didn't invoke this, but here they're saying that subtraction is its own unique operation. So I've only talked about addition. 3 plus 5 gives you 8, and 3 minus 5 would give you minus 2. And here they're actually using subtraction as its own binary operation. One of the things that's weird about having subtraction be its own binary operation, and I think it probably leads to several mistakes further down the line. So keeping it simple at the beginning actually makes it worse later. I'm going to claim that that's true, and because I'm a physicist, that means it must be true. That with addition, addition is commutative. So 3 plus 5 is equal to 5 plus 3. You get the same as answer, because that's one of the one of the interesting features of addition is that it is commutative. Subtraction is not commutative, so it is a binary operation. Does it form a group? It's associative. It seems to be associative, but it's not commutative. So 3 minus 5 is not the same thing as 5 minus 3. Okay, so it's not commutative. So one of the mistakes that people often make is, or one of the things that would help many people, including my kids as they've gone through this, is to just recognize that 3 minus 5 is actually 3 plus negative 5. So now you've taken it from an expression that is involving a non-commutative operation, and you're transforming it to an expression that involves a commutative operation. And now it's much more simple to rearrange the terms and do the math on it. You don't have to worry about this minus sign and the fact that it's not commutative. You've just written it in an equivalent form that involves a commutative operation, and now these two terms, you can switch around and manipulate however you wish, as long as you recognize that this is its own term with that minus sign out front. And so whenever people are doing, solving equations, and when you add something or when you subtract something, many a mistake would be alleviated or dodged if people looked at the expressions in this way. If they saw an expression and then interpreted it as the sum of positive and negative numbers rather than with subtraction. So if I were to rewrite an 8th grade algebra textbook, would I teach it this way? Certainly wouldn't hurt, because apparently at least this text doesn't teach it that way, and people have a problem with math. And so if you write a text that teaches it this other way, and if there were people who had fewer problems with math at the end, then that'd be better. And if you don't run the experiment, then you don't know. So that's actually an interesting thing that I hadn't considered until just now. Although I've run into it, right? I've run into it as I've tutored people, like, oh, don't think of it as minus sign, think of it as a plus a negative number. Okay, so let's see. Solution, distribute on the left. Okay, this is using the relationship between multiplication and addition, that you distribute something, like you resolve the parentheses. So that's order of operations that one is dealing with in that case. All right, is there anything else in this thing? So here's a solve this equation. It's fairly straightforward to solve something, right? You're distributing this across those different numbers, and then you're using all the inverses and stuff that go along with it. All right, let's see. Is there anything else in this? Translate and solve applications. So one of the things that this book is going to go into is what about formulas that have multiple variables? So for example, you can have, okay, here's something, the properties of equality that it's talking about. Like you can do subtraction property of equality, which I would claim is actually the addition property of equality, as long as you're using negative numbers. The division property of equality, which is the same thing as the multiplication property of equality, except you're using inverses, which means reciprocals in multiplication space. So these are, like, the world would be better, I think, if it was taught that way. Okay, so when you're dealing with a formula, now you have something different. So a formula is going to be, rather than having a series of numbers and a variable, everything's going to look like a variable. You just have to know in your head which one is the actual variable and which one are represent numbers. So for example, if you have what I did before, this ax plus b equals 0, what if a is actually the variable instead of x? So we kind of intuit in our own mind that x is actually the variable, and these a and b probably represent numbers, but it's a little confusing because they're all letters, and so which one is which? So then someone has to say solve for x. So you would say, oh, x is the variable, and a and b are numbers that are just constants. We just don't know what the numbers are, but they're not something that you can adjust. And so you would say, oh, I'm going to solve for x. This is going to be the variable, and these other things I'm going to treat as though they were numbers. And that's a standard in mathematics. This will go all the way through advanced mathematics. People will typically treat the beginning of the alphabet, A, B, and C, and D. Once you get beyond C or D, then they start just saying A0, A1, A2. They'll say, okay, these are just numbers, coefficients. And then if it gets really long and hairy, then they'll be like, okay, here are the coefficients, and they'll have a subscript. Because eventually, if you have x to the 26, then somewhere along the line, you're going to run out of letters. And so in this case, you maintain the subscript so you don't run out of letters. So it's pretty standard notation for A's and B's, things at the beginning of the alphabet to represent coefficients, and things at the end of the alphabet, which would be X, Y, Z, W sometimes, that these would be variables. But that's not always going to be true, right? Just because, what does it make a difference if it's the beginning of the alphabet or the end of the alphabet? Here's an expression. And so you might be asked, solve for B. Okay, in which case B would be the variable, and these would all be treated as though they were whatever it was that I can't think of what I was going to say, as though they were numbers, right? These would be the coefficients instead of that. Okay, so how do you solve for B in this case? Well, you solve for B by saying, okay, ax plus b equals 0. I want to solve for b, which means I want b by itself, and so I have to figure out this term right here is being added to this system, right? There's an implied plus sign here, and so what do I do to undo that? I do a minus whatever this thing is, minus ab, or minus ax. Okay, and I'm going to add that to this, ax plus b equals 0, and then I'm going to say, oh, here is an additive inverse in that thing, and I get a 0, and then I know how to do 0 plus b is going to be equal to b, and I have to do that same thing to the other side, minus ax is equal to minus ax. And look at that, lo and behold, you can solve for anything. It doesn't have to be x that you solve for. You can be told something else to solve for and work through it that way. Okay, so that's interesting. I'm not really going to worry about inequalities. We'll do that later. That's just saying, what is the set of things where a given expression, instead of using an equal sign, you're using an inequality sign, and what is the set of things that are equivalent to that? I guess let's do a couple quick examples with inequalities, because one of the things that does come up with inequalities is that when do you flip the sign, right? If you have x is greater than 5, then that's going to be, here's 0 and here's 5, and x being greater than 5 means like all the values that are greater than, in this case, greater than not equal to, so that would be an open circle, and then everything that's over here. But sometimes you'll have like x is greater than minus 5. Okay, so x is greater than minus 5 is down here. And so if it's x is, let's say that you have x is greater than or equal to minus 5. So in that case, you would use a closed circle, and it would be everything also in that direction. Okay, but now what if you have minus x is greater than 5? And this is a place where people get hung up. How do you deal with this negative sign? It ends up that you flip this inequality sign, but that is a little, how do you know when to do it? How do you know when not to do it? So let's see if we just apply the rules of algebra to this, like the real fundamental ones, what we get to. So I have minus x is greater than 5, and I want to solve for x. I want to find out what values of x have this thing, or make this expression true. Okay, so I have this minus x right here, and that's a problem because I need to get rid of this minus sign. So in general, what you do, that's a minus 1. And so the only way to get rid of a negative, a multiplicative negative, is to multiply by another minus 1, right? So minus 1 times minus 1 gives you the multiplicative identity. It gives you plus 1. Okay, and that's the thing where you have to switch this sign if you do it that way. Right, so if you multiply by a negative number, then you have to switch this sign. So minus 1 times minus x is greater than 5. Greater than. And that's where you switch this. So that would turn into a less than. Okay, so then you get x is less than negative 5. What if you didn't worry about this multiplication and you did only addition and multiplication with positive numbers? What does that do? So in that case, we have negative x is greater than 5. You have to keep this sign the same. So now I need to get x isolated on its own, and right now I've got the inverse of x right here, which is not what I want. So how do I do that? So if I want to isolate x on its own, and I have the inverse of x here, the additive inverse of x, I need to do the additive inverse of the additive inverse of x, which would look like this. Right? I have to do this right here. I got that greater than sign. I'm not multiplying by anything, so there's no sign switching. So I've got x over here plus 5, like that. These two things are going to simplify to give me 0 is greater than x plus 5, x plus 5. And now I'm going to do the plus negative 5 here and a plus negative 5 here. And I'm going to end up with a negative 5 is greater than x. Okay, so this is the equation that you get, or the inequality that you get. And then the only other thing is that because this thing matters, the order of the inequality sign matters, you have to connect it. Like those two things have to stay connected. And so if I flip the x back to the original side, with an equal sign, you can always just switch which side you're talking about. You can say these two things are equal, therefore if they're switched, they're also equal. But with an inequality, that doesn't apply anymore because the inequality sign actually has a direction associated with it. And so you have to keep the small end pointed towards the x, which means when you switch it, you're going to get an x small end minus 5, and that is the same thing that we had earlier. Okay, so it can be done. It's a little weird,